Okay, I'm going to work through whiteboard problem 26.2. So we have an engineer is designing a process for a new transistor. She uses a vacuum chamber to bombard a thin layer of silicon with ions of phosphorus. Each of mass MP 5.18 times 10 to the minus 26 kilograms. So I'll put that down here. Given the mass of the phosphorus ions, 5.18 times 10 to the minus 26 kilograms, okay? And then the phosphorus ions are doubly ionized, so the Q is 2 times the charge of an electron or proton, right? So it's 2 times 1.6, so that's 3.2 times 10 to the minus 16 coulombs. The ions start at rest at one end of the chamber, so V initial equals 0, and are accelerated by an electric field over a distance of 59 centimeters. Okay, and they strike a silicon layer with a speed of 160, or velocity of 160 meters per second. That's pretty fast. Okay, and then we have to find the potential difference. But first, let's do our diagram, right? So we want to think about this chamber. I'm just going to draw it as 2 parallel lines. And here is the silicon surface. Okay, and then on the other side of the chamber, we're going to start with our positively charged phosphorus atoms, and they're going to be accelerated, right, to hit the silicon layer. So if they're going to be accelerated in this direction, I like to think about it as, what is the field that could create this, right? So if the silicon was on a metal plate that had a negative charge, that would draw the phosphorus to it. And we could do the same on this side to make it even more effective. We charge this side positive, and that's going to push the phosphorus away. So there will be an electric field in here, right, that's going to be pointing in this direction, showing you the force that the positive charge would feel. And we were given this radius over which the charge is accelerating. Okay, so that's kind of a visual of what's happening. And then the phosphorus is going to get down here, right, and it's going to be moving fast and then bombard the silicon. Okay, so for part A, we want to find an expression for the change in potential, delta V, in volts. Okay. And so remember, when we talk about energy and potential, the positive charge is high potential energy here and low potential energy here. So this is going to be high potential as well. High V and low V on this side. Okay, so it's telling us about we know the speed, we know, there's a change in potential. So think about this in terms of conservation of energy, right? So we can say our initial energy is equal to the final energy. Okay, and we'll just put in the terms that we could have right now. This is kind of a electric potential problem. So we can have potential energy, and we can have kinetic. We'll say that's initial. We can have some kind of final potential energy, and a final kinetic. Okay, and normally these things are happening so fast that we don't need to worry about the effect of gravity over here. So we're not going to worry about a change in gravitational potential energy. Okay. So let's move these to the different signs, right? So we have here, if I bring my K final minus K initial, and then over here I'd have potential energy initial and minus potential energy final. And usually when we do deltas, we do final minus initial. So I'm just going to say that's the negative of my final minus the initial. And that equals my final minus the initial kinetic energy. And I should have done this initially, but we're starting from rest, so this term is 0. You know that? Okay, and our change in potential energy, we have looked at this before. That's our charge times the voltage that we're moving it through. So we have negative Q delta V equals K final. And this we know is 1/2 mv squared. Okay, that's our kinetic energy. So again, be careful with the, I'm going to try and do like a little script V for velocity versus capital V for voltage. And this is what we want to find, right? So we have delta V, which would be our V final minus V initial. Equals m V final squared over 2Q, and then we have a negative sign. And so we have to look at the problem and see if it wants the absolute value or not. But our final, we said this is going to be low, so if we did a final minus the initial, we'd get a negative answer. We should get a negative answer. So we can plug in values for that, right? And everyone's going to have a little bit different values, so I'll leave that just as a variable form. Okay, and then for part B, it says find the average electric field strength in volts per meter. Okay. So find the electric field. Okay, and so we did this in class. If you know potential and change in potential, you can calculate the electric field. So the electric field is negative change in potential over change in distance, right? If we're just talking about the average value here. And this is in a particular direction, yes, let's say. And this is just a one-dimensional problem. So we know the distance over which this is changing, right? We're given that. We also know the change in potential, so we can figure out our electric field is negative change in my potential, which is going to be negative mv squared, v final squared, over 2q. And then we're dividing by our change in position, which is 1 over r. Okay, so I get two negatives here, so I get mv final squared over 2qr. Okay, so that would be my expression for electric field. I'll just write it again here. And again, everyone's going to have different numbers, so we can just leave that in variable form, and you can adjust as necessary. And then part C says find the force. Okay, so if you remember the relationship between force and electric field, you know, force is Q times the electric field, or electric field is the force per charge. So we know electric field, we want to find force. Now we just have to multiply by the charge. So the force is Q times E. And so that would be Q times mv final squared over 2qr. And so my charges cancel out, and I get mv squared over 2r is my force, the average force. And that's it.